Okay, so as we have discussed before, the goal of these videos is to help us understand better how to what are the different techniques for solving problems in dynamics, what are some of the approaches that one can take in solving dynamics, and what are the general procedures, what are the general techniques. So in the last two videos we have looked at the problem of our disk, which is translating and rotating as it moves on a horizontal surface. And we have one of the questions that we asked was to find the velocity of a point on that disk. So to be specific, the problem that we were discussing is the following, where here is a disk, and let's say that the disk is of radius capital R, and let's say that there is a point P which makes a certain angle theta, where PC, C is the center, so the line PC makes an angle theta with respect to the vertical drawn through the center, and the disk is has a motion which involves a translation of C as well as a rotation. So the rotational speed is theta dot, and we have selected our x, y, z frame like this, with the origin O shown here, and the center of the disk is at a distance x at a given instant, at an arbitrary instant, and the point P is at a distance of d, and we have asked the question, what is Vp, or determine the value or the expression for Vp, and we have solved this problem using two methods. If you look at the previous two videos, and one was basically differentiation of position of P. So that was one method that we showed, and the second method was use of a relative velocity of P with respect to C. So we have, and the result that we got with both methods was that Vp is equal to x dot plus d theta dot cosine theta I minus d theta dot sine theta j, where I and j are the unit vectors in the x and y directions shown here. So this is the problem that we have solved. Now, since the discussion is on techniques of dynamics, dynamic analysis, or let's say dynamics analysis, at this point it may be a good idea to just step back and think what we have done, and in solving this problem, and kind of try to identify if what we have done in the past two videos gives us a practice that we could follow to understand dynamics better, to feel more comfortable in solving problems in dynamics. So one of the things that I have seen helpful for me, and perhaps this could be helpful to many students and researchers of dynamics, is that I have seen that if I try to solve a problem using multiple methods, so I take the same problem but I try to solve it in 2 or more methods, what happens is that it reinforces our understanding in some of the fundamental concepts. So I have found out this approach of trying to solve a problem using different approaches. This I have found to be quite helpful. It is almost like taking a particular problem and looking at it from multiple angles. It not only reinforces our understanding in the fundamental concepts of dynamics, but I think it also gives us a better appreciation or better understanding of the problem. So when we say try to solve using different approaches, what I mean is maybe different techniques. For example, over here we used the differentiation of position p directly to find the velocity as our first approach, and then the use of relative velocity, both of which gave us consistent answers. And another way to solve a problem using different approaches is to try different coordinate triads. So when we say coordinate triads, we mean these XYZ triads. So, and we will demonstrate this in problems to come, in the videos to come, where you will see that certain problems in dynamics are more readily solved using certain triads than others, because in certain triads the expression of some of the vectors become much more easier than the expression of those vectors in using other triads. So this is another way, using different coordinate triads to solve the same problem is another way to basically practice dynamics and to understand dynamics better or kinematics better. You could also try different reference frames to solve the same problem. Again, this is something that we are going to come across more in future videos, but you can formulate the problem as if you are viewing a certain motion in multiple reference frames, right? So for example, a quick example is in a fixed reference frame, or also in a reference frame that is just translating with the center of this disk, the velocity of p with respect to c is a circular motion, right? So if, let's say, you are on a reference frame which is translating with the disk, right, then the motion of p with respect to c would be just a circle. And that would actually also be true when you find the motion of p relative to c in a fixed reference frame. Okay. Now, if you studied the motion of p with respect to c on a rotating frame, that is a frame, let's say, that is fixed to the disk, so as the disk turns and moves, the frame also turns and moves with the disk, and it is rigidly fixed to the disk. If in that reference frame the point P would have no motion with respect to C, right? So this is, I mean, you can do some quick calculations and show that, let's say there are two people that are standing on the face of Earth, right, and no one is moving. Okay, of course the Earth is rotating. So if one person looks at the other person, both standing on the Earth, both not moving, then what would be the relative motion that one person would record with respect to the other person? It would be 0. And that's because the reference frame is fixed to the Earth and the Earth itself is moving. However, you can show through some quick calculations, if you tried to find out what is the velocity of the first person with respect to the second person, okay, as measured from the sun, that velocity would be different. Okay, because from the sun you see person A having a certain velocity and person B having a certain velocity, and their velocity directions are a little bit different because they are standing on a circular surface, and so there would be a relative velocity between the two. So the relative velocity, where you look at it, in what reference frame you look at it, can lead to different interpretations, and you can use those different reference frames to also formulate a problem or solve a certain problem. So that's the third approach, and the use of different reference frames is also something that will come up quite frequently in our forthcoming videos. Now this is one of the very important and useful approaches to understand dynamics, is to try one problem using multiple methods. Another thing that I encourage students, researchers to do when you're dealing with dynamics is, after you solve a problem, to interpret the results. So interpretation of results. For students that are serious about dynamics, that want to get a very clear understanding of dynamics, I think interpretation of results after solving a problem is a very important part. So it's not about just finding the result and maybe matching the answer with the answer given at the end of the book and that's it, but you should try to see what the result is telling us, right? So essentially what we are saying is, what are the results telling us? So that's the question basically that we can ask. You can also take this question and pose it in the following way, that do the results agree with our intuition about the problem? So we often, when we solve a problem in dynamics, we have an intuitive understanding of the problem, and one thing to do is to see if the results are agreeing with that intuition. Now this, however, is something which I would put a question mark, because depending on the problems, our intuition can fail in dynamics. If given a particular problem, depending on the difficulty of the problem, unless you have a very clear understanding of dynamics, unless you are extremely gifted and you can understand the inner workings of the problem very well, then your intuition can tell you something more accurate. But for people that are trying to understand dynamics through hard work and diligence and trying to get better at it and improve our understanding, often intuition can fail us. especially in dynamics and especially in rigid body dynamics, where motions can get really complicated because of the way different coordinates they interact with each other, even for a single rigid body. So that's why I put this question mark, because intuition can sometimes fail us. So what do we do then if intuition can fail us? Well, one way to interpret the results is to ask the question, are the results predicting some basic observations? Accurately. So there may be, although some of the results may be more complicated to understand through intuition, other results could be that are quite basic, and there, you have a certain higher level of certainty that this system is going to should have this kind of a characteristic or this kind of a behavior. So for those very simple fundamental results, you can try to see if those observations, those basic observations, are being predicted by the results. So are your results predicting those very basic observations correctly? And so that's where another interpretation of results comes into play. Are our results correct? Are they predicting, making some correct predictions, even for very simple observations, right? And once you have done that, and once you have a certain level of confidence with respect to your analysis, then you can go to the more scientific and engineering question of what else can this result give us? What kind of predictions can I make from this? Okay, are there any engineering benefits that I can gain out of this system that I am analyzing? So anything new that the results will tell us. So any new insight that the results give us, right? So that's another aspect of that's the final aspect. Once you have understood the results, once you have a certain level of confidence, then at that point you use the results to predict something that goes beyond, and that's where new developments, new knowledge, or new ideas in engineering will emerge from. Okay, so now let us see how we can apply this idea of interpretation of results for this particular problem, right? So for this particular problem, let me just go to a new page so that I can keep this problem in view. While I make some notes. So recall that the velocity Vp was x dot plus d theta dot cosine theta I minus d theta dot sine theta j. Okay. You can look at the velocity this way, or you can also look at the velocity as x dot plus d theta dot times cosine theta I minus sine theta j. Okay. The second way of looking at this result basically splits it to two parts, where you have the first part as the velocity of c and the second part as the velocity of p with respect to c. The first way of writing the result basically takes the entire velocity vector and resolves it along the x and y directions. Okay. Now, in general, if I take this second equation, what this is telling me is that the velocity at any given instant of this point P, if this is my point C, this is the point P, then there is one component of the velocity which is x dot, and the other component, let me just draw a vertical line through the point C. The other component d theta dot is perpendicular to CP. So this is d theta dot and it's perpendicular to CP, and this is the velocity component that comes from the fact that the disk is turning, is rotating. So there is one component due to the translation of the disk and one component due to the rotation of the disk, and the net velocity of P is due to a vector sum of these two, and in fact the angle between these two vectors is theta, okay, because CP is making an angle theta with the vertical, and you can show through geometry that if CP is making an angle theta with the vertical, then this angle is theta, and so the net velocity of P is this guy, right? So that's the velocity of P. It is the vector sum of x dot and d theta dot, okay? So and this is the same vector addition has to be done at no matter where the point P is as the translation and rotation is happening. So for instance, when the point P is over here, then still we have that x dot, right? We have that x dot. And now we have our d theta dot, which is still going to be perpendicular to CP, pointing this way, because P is still turning clockwise, so this perpendicular is still there. And so, just for the sake of clarity, let me just use a different color pen to show the vector sum. So if I complete the parallelogram of vectors, then at this point the velocity of P is going like that, right? It is the vector sum of x dot and d theta dot. So you have a vectorial representation which tells us how the point P, its velocity is going to change as the disk turns, right? Keep in mind that in this problem we are considering P to be at a constant distance d from the center C, right? So this is one insight. Basically it is telling us that it is giving us it's giving us a vector summation interpretation of what the velocity of P is, depending on where P is at a certain point at an arbitrary instant. Now there are other questions that we can ask. For instance, is there a point or location or condition under which Vp is equal to 0, right? So if we ask this question, okay, so let us consider this question for a second. Is there a condition under which the velocity of P is going to be equal to 0, right? Considering that P is at a distance of d from the center and the disk is translating and rotating. So to understand that, Vp equals 0, what does that imply? It implies d theta dot sine theta must be equal to 0 and x dot plus d theta dot cosine theta must be equal to 0. So both these two must be true, because we are saying that a vector is equal to 0. That means all of its components individually must be equal to 0. So now let us take a look at under what conditions would this velocity of p be equal to 0. So one condition that you can see from here very quickly is Vp is equal to 0 if theta dot is equal to 0 and x dot is equal to 0. And that is a very trivial case, because indeed x dot equals 0 means that the disk is not moving towards the right along the x-axis, and theta dot equals 0 means that the disk is not spinning. So essentially we are considering a fixed disk, and so if you have a fixed disk, then the velocity of the point p is of course going to be equal to 0, right? So this is kind of a trivial condition. Another condition that you can come up with is Vp is equal to 0 if let's say d is equal to 0 and x dot is equal to 0. Okay, so d is equal to 0 and x dot is equal to 0 is another condition under which the velocity of the point p is going to be equal to 0. And if you think about that, that's also a pretty simple situation, because that's the situation where the point p is basically at the center, because d equals 0 means p coincides with the center of the circle. So when you are at the center, and if the circle is not translating or the disk is not translating, then c is not going to have any velocity, because just the spinning of the disk does not give a velocity to the point c, right? If the disk just spins but does not move, then the point c does not have any velocity. For the point c to have a velocity, you not only you need the disk to have some horizontal motion in this problem. So that is also a relatively simple case. Now the third case is Vp is going to be equal to 0 if for instance, now theta, keep in mind, is going from 0 to 180 degrees to 360. After that the angle theta just repeats, right? So 0 degrees is when theta is vertically upwards, or sorry, p is vertically upwards. 180 is when p is vertically downwards, and 360 is when p is back up vertically upwards. So after that the angle theta just repeats. So if I have the scenario where theta is equal to 180 degrees, or if it is 0 degrees, so think about it, when theta is equal to 0 degrees, then the velocity can be 0 if x dot plus d theta dot is equal to 0. Okay, so if theta equals 0 and x dot plus d theta dot is equal to 0, or if d theta dot is equal to negative x dot. Right, so that is one condition. Now this condition, while theoretically this can happen, and I'll take a look at this condition a bit more, but I think a more practically relevant condition is if theta is equal to pi, which is 180 degrees, and when theta is equal to pi 180 degrees, d theta dot becomes equal to 0. D theta dot sine theta becomes equal to 0, so this part is fine, and then x dot minus d theta dot becomes equal to 0, which means that here d theta dot is equal to x dot. Now this leads to a very interesting condition. Consider the case, and it's a very practical condition, so consider the case when the disk is rolling without slipping. Consider the case where the disk is rolling without slipping. Okay, so the disk rolls without slipping, and if you consider that case, essentially what is happening is let's say this is the point P, this is C, this is D. This does not readily tell us that this is the condition of rolling without slipping. There is an additional condition where it leads to rolling without slipping. Now consider the case when the disk is rolling without slipping. Consider 2 points. A point Q that is on the disk, okay, but at the contact point between the disk and the ground, and a point Q prime, okay, Q prime, which is on the ground at the contact point between the disk and the ground. So you would agree that VQ prime is equal to 0, right? Because it is the ground, and in our problem we have not considered the ground to be moving. So VQ prime is equal to 0. Now if the disk is moving, is rolling without slipping, so therefore for rolling without slipping, VQ must also be 0. Right? Because if it is non-zero, then the point Q, which is a point on the disk, would have a relative motion with respect to Q prime. Right? So when we are imposing the fact that the disk is rolling without slipping, we are by definition saying that VQ must be 0 if the ground is not moving. So assume that the ground is not moving, then VQ must be 0. Now what is VQ according to our formula, according to what we have derived here? So VQ is going to be VP, but substitute D equals capital R and theta equals 180 degrees, which is pi. Right? So what is VP? Well, VP is x dot plus d theta dot cosine theta I minus d theta dot sine theta j. So in this VP we need to consider, we impose these two conditions. So impose the condition here that d is equal to capital R and theta is equal to 180 degrees, which is equal to pi. So if we did that, then what we get is VQ is equal to x dot minus R theta dot I and since theta is equal to pi, this part is equal to 0. And so this must be equal to 0, which means that x dot must be equal to r theta dot. So we see that the condition for rolling without slipping is x dot equals r theta dot. And if you go back to your basic kinematics, you will see that yes, that agrees with the condition for rolling without slipping that we typically impose for a rolling disk. That is, the forward velocity is related to r times the angular velocity, and that is also evident from here. So here is another confirmation that tells us that what we have derived is indeed correct, because if we impose rolling without slipping, then the corresponding velocity of p that we get at the circumference of the circle, when we impose that p is at the circumference, that is d is equal to r, and when the point p is then in contact with the ground, we should have a zero velocity. And if we impose the zero velocity, we get the condition for rolling without slipping, right? So that these are some of the interpretations, these are some of the results that these are some of the predictions that we have, and the rolling without slipping condition matches well with what we typically see, how we typically formulate rolling without slipping in kinematics. There are a couple of other things that we can also observe. So let me just show what the velocity of the point P would look like under rolling without slipping when the point P is at the circumference. So let's say this is our disk, and here again let me show the vertical line. This is the point C. Let's say that we consider the case where the angle theta is 90 degrees and the point P is at the circumference. Rolling without slipping is happening. So here the velocity due to the translation is x dot is equal to r theta dot, and so this is our point P. It is at a distance of capital R, and the velocity that the point P has due to the rotating motion of the disk is also r theta dot, right? Remember that this is going to be always perpendicular to the CP line, and so this vector is going to be, these two vectors have the same magnitudes. So this vector is going to be a vector which is at 45 degrees angle from here, and if you draw a 45 degree angle from this point, it will pass through the top of the circle at this instant. So, and the magnitude of this vector, you can imagine it's going to be r theta dot here, r theta dot here. So it is square root 2 r theta dot, right? And this is at 45 degrees from the horizontal. So when you are considering the peripheral point and when the point is just ahead of the point C, its net velocity is square root 2r, and it makes an angle of 45 degrees with the horizontal. Similarly, when you consider the point P at the top, there you have the velocity of the disk itself, the translational velocity, which is r theta dot, and on top of that you have the velocity that is due to the rotation, another r theta dot. So the net velocity of P is 2r theta dot. So at the top the velocity is 2r theta dot. Here the velocity is 0, Vp is equal to 0. So often when we study rolling without slipping of a wheel, this point is considered as the instantaneous center, which is when the wheel is rolling without slipping. And if you, for instance, consider the point P over here, then it has again two components. You have the r theta dot, which is due to the translation of the disk, and then because of the rotation of the disk you have the vector r theta dot here. I should have probably drawn the vector like this, because if you drew the and then the resultant of these two would now make again 45 degrees. The magnitude would be square root 2 r theta dot, and it would make an angle of 45 degrees, which would again pass through the center. So there is some interesting geometry here that shows up. So this is again telling us, giving us some interpretation of the results. Just taking the same the solution that we have for the velocity of p, and then applying it at a certain distance and at different angles to show what kind of velocities we get, gives us an idea of what the velocity of the point p, how the velocity of the point p changes as the wheel moves on the horizontal surface. And this particular is the scenario is the case where we have rolling without slipping. So that's it for this video, and we are going to look at some other aspects of this problem in the upcoming videos. So that's it, and we will post more material shortly. Thank you.